space shuttle flies with a typical altitude of 300 kilometers above the surface of the Earth. The radius of the Earth is 6,328 kilometers, and the mass of the Earth is 6 times 10 to the 24 kilograms. A, what is the velocity of the shuttle? And B, what is the period of the shuttle's orbit? This is a case of circular motion, and circular motion is a force problem. And the first step in every force problem is to draw a free body diagram. This dot will be used to represent the space shuttle itself. When we choose to name any one force acting on the space shuttle, gravity is the first one that comes to mind. And because the space shuttle is not on the surface of the Earth, we don't use the formulation of m times g for the strength of gravity. Instead, we use the full Newtonian formula of capital G. Lowercase m will be the space shuttle, uppercase m will be the Earth itself, and r squared will be the radius, which means the distance from the center of the Earth to the location of the space shuttle. Often in a circular motion problem, students become tempted to add an additional force to their free body diagram, which they call the centripetal force, having been taught this by their instructor. However, centripetal is not a force. Centripetal is a direction. In standard force problems, you sum forces in the x direction, setting them equal to m times a sub x, and you sum forces in the y direction, setting them equal to m times a sub y. But you do not add an x force in the x direction or a y force in the y direction as an additional force. Similarly, you do not add a centripetal force to the diagram, but rather you sum the components of forces in the centripetal direction and set them equal to m times the acceleration in the centripetal direction. Since the space shuttle is above Earth and does not experience a surface, it is not on a string, the only force in our free body diagram is gravity, and we have a one-dimensional and even one-force free body diagram. The way in which we analyze this free body diagram is the same way as always. We align our coordinate system with the acceleration. Whenever an object is turning in a circle, it is accelerating, and the direction of its acceleration is toward the center. So since our diagram represents the space shuttle in the moment shown in the picture, the center will be downward, and that will be what we call the plus direction. Analyzing the centripetal direction, we find that there is one and only one force, and this force is entirely in the centripetal direction, and that force is the gravity, g, mass of the shuttle, mass of the Earth, over r squared. The sum of all forces in any direction is equal to the mass times the acceleration in that direction. The mass of the space shuttle, we'll use lowercase m to represent that. And then we ask ourselves the question. This question always has the same answer. Is there an acceleration in the centripetal direction? And the answer is yes. If there's a centripetal direction, there must be a circle. If there is a circle, you are changing direction, and that is a change in velocity, and that's an acceleration. The strength of the centripetal acceleration is velocity squared divided by the radius, where this radius is the radius of the circle around which you turn. The formula produces a very nice cancellation. The mass of the space shuttle, lowercase m, cancels on both sides, and we're almost ready to solve for the velocity at which the space shuttle moves. However, there is something we need to be careful of. Physicists very frequently use the letter r, representing the word radius, in formulas. However, for every such formula, we have to be extremely careful about what is meant by the radius. Typically, it is either the distance between the centers of two objects, or it is the radius of some circle. In the case of the force, as we mentioned previously, it is the distance between the centers of the two objects. So going back to our diagram, we'll notice that the center of the Earth is represented by this green dot. The space shuttle is up there, and so the radius for the gravity formula is this distance. Not the radius of the Earth, 6328 kilometers, but in fact the sum of the 6328 kilometers for the Earth's radius plus another 300 for the altitude of the space shuttle. Similarly, when we ask the question, what radius goes into the v squared divided by r formula, that radius is the radius of the circle around which the object is moving, and that radius is also equal to the sum of the radius of the Earth plus the altitude of the space shuttle. It isn't always true that the radii in both formulas will mean the same thing, but in this case it is. So, for that reason, we get a second cancellation in our equation. The radius on the right, being the same as the radius on the left, indeed cancels, leading us to the following formula for the velocity. The velocity of the space shuttle in orbit is the square root of Newton's gravitational constant, which is 6.67, 10 to the minus 11, the mass of the Earth, which is given, the radius, which is not 6,328, but is in fact that plus another 300 kilometers. Converting this to meters, it will in fact be 6,628,000 meters. Plugging in the numbers, we get the result. 7770 meters per second. For part B, we've been asked what is the period of the shuttle's orbit. Well, in fact, period is the amount of time that it takes to make an orbit, and this is very easily related to the velocity, because velocity is always distance over time. And what I claim is that every orbiting object goes a distance of 2 pi times the radius in an amount of time which is equal to the period. You may use a different symbol for period in your book. Here I'm using a lowercase Greek t. So the velocity is the circumference per period, yielding a period of 53.67 seconds, which is the same as 89 minutes, or about an hour and a half.